Hello, everybody. Welcome to the Azure Files session. Today, we will be going over some of the learnings that we have gathered over time and some of the challenges that we have gone and solved along our journey to build one of the largest file systems in the world. My name is Reena Shah. I'm a product manager on the Azure Files team. I've been on the Azure Files team for the last 8 years. With me is Utsav Mohata. He is a principal software engineer, one of the very early members of the Azure Files team, and he's been on the Azure Files team for 12 years now. From the agenda perspective, we will look at it from the customer perspective and see what are some of the cloud file workloads that we are seeing and some of the interesting cloud expectations that we see that customers bring to us. And then we will deep dive into the interesting challenges that we have tackled along the way in areas of high availability, performance, and security. And then we will also cover the REST interop, which we have seen to be a pretty interesting one because of the interest we have in terms of our ISV scenarios. So file system workloads, not something new. File systems, SMB, NFS, they have been around for decades. And along the way, customers have used it in a variety of different workloads. Some workloads require end-user access. Some workloads require application access. Some workloads are requiring various platforms. Some are on Windows, some are on Linux, some are on Mac OS. So file systems are used for shared storage across multiple platforms, across multiple workloads. Any guesses which of the workloads are moving to cloud? All of them? Yes, all of them. So, and when they move to cloud, of course, it's a big change, right? So when customers are moving to cloud, they expect that the cloud is going to give them some benefits. First benefit is, unlike on-premises, like no maintenance downtime, no windows to go and apply patches and bring up your file server again. All of that needs to be always on, always available. The SLAs that we provide have to be 99.99, and guess what? That's not enough. We are being asked for more. So that uptime availability has to be really, really high. Customers do not migrate their workloads to cloud overnight. It has to come in phases. And while they are in this phase of doing an on-premises to cloud migration, they are in this hybrid mode. And the expectation is that the workloads are being supported both on the on-premises and in cloud simultaneously in some hybrid fashion. And typically, these are traditional workloads, right? They are written with SME and NFS and file systems in mind. However, when they move to cloud, we want the same workload, same functionality that was being offered on premises, and at the same time has a modern component to it. And then because Azure Files is a cloud file service provider, the economies of scale that we get by having the development and the hardware cost savings, we need to pass it on to our customers. So cost savings is top of the mind when moving to cloud. So how did we solve the workload diversity and the expectations? So we had to go and solve it with multiple solutions. So for the on-premises access, so think about general departmental shares or branch offices collaboration, we offer Azure File Sync, which is an on-premises cache of your data which is sitting in cloud. So your Windows file server on-premises becomes a cache while all your data is still sitting in the cloud. And that's the solution that customers want when they are looking for hybrid access. Next is the industry-specific apps and in general the apps which are using the SMB and the NFS protocol. And for that, we implemented SMB and NFS protocol ground up and offer that natively in the cloud. And then when customers are migrating certain kind of workloads like AI/ML or cloud native workloads, want to re-platform their service to a containerized service. So for that, we offer the Kubernetes service in cloud. And for connecting the Azure Files to the Kubernetes service, we require something called as a CSI driver, which provides the semantics for how to connect from a containerized application into the file system. So we were one of the first ones to write a CSI driver according to the spec. And then on top of that, we need to provide value-added services like backup and caching and migration. So all of that, for all of those, we typically see customers and partners using REST APIs. So looking at it overall, when we started with SMB protocol, and we started with SMB protocol on hard disk. We moved and we provided SMB protocol on premium. And as I mentioned earlier, it is highly available because it is deployed on a distributed platform. And this enables customers to bring their traditional workload into cloud. We provide Azure File Sync for hybrid workloads, and the management of your file system completely moves to cloud because your backups are happening in cloud, your replication is happening in cloud. And for the cloud-native workload, we provide access semantics for accessing from AKS or any other Kubernetes-based deployments, and REST for the value-added services. So with that, I will hand it over to Yurtsav, who will go into the deep dive.
Thank you, Reena. So I have been with Microsoft for the past 12 years, and I've been working on Azure Files. Just before we go into what Azure Files is, I wanted to share what it is not. It is not a simple rehost of a Windows or a Linux file server. It is a cloud-native, scalable implementation for distributed file storage, built ground up. It's a fully managed file share, and it allows customers to seamlessly migrate their mission-critical applications to the cloud. Being the world's largest distributed file system and having implemented both SMB and NFS4.1 stateful protocols, it brings with it a unique set of challenges and performance optimizations and improvements that we had to do. But before going into that, I wanted to briefly summarize what the Azure Storage architecture is, because to get that highly available, consistent, durable consistencies, we have actually built the Azure Files for both SMB and NFS4.1 on top of Azure Storage. So a customer can access their data via an endpoint, which is essentially a storage account name .file or blob.co.windows.net. They get an IP address. They actually go through the load balancer to one of our front ends. Our front ends are pretty much their protocol endpoints, and they deal with authentication and authorization, along with some metrics and logging that the end user can actually view through the Azure portal. From the front end, the request comes to the partitioning layer. Partitioning layer is a massively scalable key value store. Essentially, it understands what a blob is, what a file is, and provides the consistency which for Azure Storage. And for every backend node which is there, it works on a specific key range, and that backend node is responsible for serving traffic for that specific key range. From the partitioning layer, the request comes to the stream layer. Essentially, stream layer deals in bits and bytes, and every data that is sent to the stream layer is written 3 times. We maintain 3 copies of our data, and the stream layer is an append-only distributed file system, which is the backing store for Azure Storage. So we are built on top of that. We reuse the Azure Table and Azure Blobs as the backing store. We use Azure Tables to maintain our metadata, and we use Azure Page Blobs for writing the data for our files. There's another concept of a group of tables for the same key range, and Azure Table allows us to associate a set of tables as a group, and we can make transactions across this set of tables with an asset semantics. So let's take an example of a file exists in the Azure File Cloud, or Azure File Share. You want to open a handle against it. So you will go and update one of the main tables, which is the entity table. You will actually go and update the second table, which is a handle table, for the specifics regarding the handle. And if for SMB, if you open an exclusive lease, so we maintain state for the lease table also. So all these multiple tables which are there, which are bounded by a specific key range, can be updated in a single transaction, giving us asset semantics. This aligns well with what we wanted to do for Azure Files. And because we are a distributed file cloud system, which are hosted on multiple nodes, which can go up and down at any given point in time, maybe due to upgrades in our code pipeline or due to an OS upgrade going on, we need to maintain state in such a way that a client can connect to one of the front ends, and then if that front end goes down or a connection gets disconnected, then the client can connect, or rather reconnect to another front end, and we are still able to serve traffic. That is, we are highly available. So we tier our data by the durability requirements to help with reconnect and reclaim. I am generalizing here, but Azure Files is both for SMB and NFS 4.1. Both of them are stateful protocols. So let's talk about the Azure Files architecture. So internally, the SMB and NFS 4.1 are different protocol heads. They have a shared design and implementation and are only different when the protocol requires them to be separate. Going through the same workflow of how a request is served for Azure Files, we get the account name.file.co.windows.net, we resolve it, go via the load balancer to one of our front ends. Azure File uniquely offers you to be able to access your data via two stateful and one stateless front ends. So SMB front end, let's take an example of a request which comes for an SMB front end. That goes to the partitioning layer, and the same thing, the data gets persisted 3 times. So that's the regular workflow which we have. What I was talking to you previously about the tiering of data, right? That's what I wanted to highlight on this slide, which is the ephemeral state. Now, what is ephemeral state? It's temporary and volatile state which does not need to be persisted across sessions or across reboots of node. For example, that would be your file ID.volatile credits for the connection, the TCP socket details. For NFS, it would be state ID. And on the back end, which is a combination of our partitioning layer and the stream layer, we maintain durable state. The main reason to maintain durable state is it should actually help us in our reconnect scenarios. Right? So let's look at the durable states that we have. That's your persistent file ID, session ID, handle ID, and byte range locks for NFS. Essentially, whatever would have been in memory or RAM for a file server needs to be persisted by us, so that if a client were to disconnect and reconnect through another front end, we are able to reconnect them transparently and seamlessly and continue serving traffic. So over here in this talk, I wanted to discuss 3 areas where we have made some interesting optimizations as well as fixes, and the challenges that we have faced in our journey. So one of them is high availability, perf, and security. Right? So for high availability, as I was talking to you before about restarts and reconnects, right? We are made up of hundreds of nodes, and Azure File Service, we can restart due to upgrades, deployments. So the solution, as I discussed previously, was tiering of data. The SMB protocol lends itself beautifully with persistent handle support for 3.0 and above, because that gives us some durable state that we can maintain on our backend and get transparent, and a client can transparently fail over from one front end to another front end when one of the front end restarts. So just a diagrammatic representation of what I mean here is, assume client A and client B are connected to the same share. They will, via the load balancer, may fall on different front ends. What if there is a network interruption or disconnect? And at that point in time, there is state which is maintained in the Azure table in blob storage, and the client will just seamlessly reconnect because of the state which is maintained on our end. Live migration. Now that's something which is really interesting for me. So I want to paint a picture for you guys. A customer account is held on a storage cluster, right? It's hosted on a storage cluster, and there are multiple storage clusters in a region. Now, the storage account may need to be moved from one storage cluster to another storage cluster due to multiple reasons. Load balancing, maybe we are decommissioning old hardware. So we need to move customer data from the old cluster to the new cluster. Now that process is called account migration for us. And migration has multiple phases, but the most, at a high level, the four important ones are: we copy data over from the source cluster to the destination cluster. Once we do that, we actually update the DNS mapping such that the account name.file.co.windows.net is pointing to the destination cluster. Then we issue a disconnect from the server on the connection with the client. And if the client refreshes their DNS entry, they will now land on the destination cluster and continue serving there, and the storage stamp will continue serving their traffic. There are interesting challenges when the client do not refresh their DNS entries. As a result of it, we have another stage which is called redirection. And all of this is supposed to be transparent to the user. This is an internal Azure Storage migration. Now, the issue that we see is, for example, old Linux clients, right? Their file IOs will start failing with host is down or permission denied failures. Now, before I go and share how we solve this problem, I just wanted to discuss the two happy path scenarios that we have for account migration. So a client is trying to connect to an endpoint via the load balancer. It is going to come to one of the front ends. It will then serve the Azure Storage stamp. The source cluster will serve the traffic, as we have already discussed in the previous slide. Now, due to some load balancing reason, we decided to move the data for this customer from the source cluster to the destination cluster. We persist that data in the partitioning layer as a row, which says that this account name now is going to be served by this destination cluster. We move the data over. Once we have moved the data over, we are going to update the DNS mapping, and then we will disconnect the connection with the client. Now, if the client refreshes the DNS entry, it will get the new IP address, in this case, which is 172.a.b.c, and will be served, and we will serve its request through the destination cluster now, because that's where the client will end up connecting. It's just the same workflow again to serve a request. Now, this is the redirection which I was talking to you about. Let's go through the same workflow again, wherein the client is connected and we are serving requests to it. For load balancing reason, we decided to move the client's data over from the source cluster to the destination cluster. We are maintaining that metadata in the partitioning layer on the source cluster. We update the DNS entry and now disconnect the connection with the client. Now, the client at this point has not refreshed its DNS entry. So it will come back to the source cluster. Via the SMB front end, it will go to the partitioning layer, find that it's the traffic or the data for this client or account name resides on a different cluster. we will then redirect that request from the source cluster to the destination cluster, and then we serve the request. The response goes back from the destination cluster to the source cluster, which then goes back to the client. Now, in this picture, this metadata which is persisted on the source cluster's partitioning layer has an expiry time. If the client, as long as this connection is established, we will continue serving requests for the customer through this layer of redirection. You can see how if the connection now gets disconnected and if the client does not refresh its DNS entry, it will end up coming back to the source cluster, and we do not have that record anymore as to where to redirect their request. And as a result of it, the client started seeing host is down or partition or host is down or permission denied failures. So the solution here, what we did was we maintained an in-memory cache and extended the window for which the service would continue the redirection. And with our friends in the Linux community, we submitted fixes to the mainline Linux kernel to update the DNS entry periodically and not maintain the stale entry over there. So the fix that we suggest to customers are you might want to upgrade your client OS with the fixes. The benefit of the server-side changes which we made was we got a reduction of CRIs by like 99%. And in future, we want to contribute to the community for NFS4.1 also, similar to how we are contributing in the Linux community. So that was pretty interesting. Now moving on to the next focus area is performance. And here we actually approached it from both sides, client as well as server side. The main focus areas over here are improvement of metadata latency for metadata operations, along with increasing the client throughput. And the main one for any cloud file system is to reduce the number of round trips. Let's focus on improving the latency for metadata operations. So there are workloads which do a high volume of metadata operations against an SMB premium file share, which will benefit a lot because of this. These workloads tend to generally be DevOps pipeline related processes or virtual desktop infrastructure ones. Let's see what the architecture or the changes we made for that is. This is again how a request gets served by Azure Files. We have a stateful protocol for SMB frontend and NFS v4.1. The request comes to the partitioning layer and gets written 3 times on the stream layer. For even a file open or a file create, we persist that 3 times on the disk at the stream layer. So you can see how that may add up or contribute to latency. The biggest benefit which we get of leveraging Azure Storage as our architecture and building on top of it is what Reena already pointed out, is the cost efficiencies that we get with a shared architecture. And the architecture might not be optimized for all types of workloads, but all different services have made their own set of improvements on the shared architecture. So what we did over here in the partitioning layer was we added an L1 in-memory cache, which is backed by an L2 persisted cache. And that's how we serve metadata operations like create, open, close. What this means is we no longer need to persist these operations on the disk 3 times, which helps with reducing latencies significantly. So what we can see here is we saw an improvement of up to 55% lower P50 metadata latency and up to 3 times more metadata operations at scale at high QD. There is documentation listed over here where you can find additional information. Coming back to increased throughput, both the protocols, SMB as well as NFS, has something for multi-channel as well as NConnect. Now, what do both of these features do? They actually enable clients to use multiple TCP connections to provide higher performance for both throughput as well as IOPS. They are both, all the 4 connections, the TCP connections, are part of the same session. And as a result of it, in the previous world where you would have a single TCP connection, if that connection gets disconnected, and assume you had 100 file handles open on that specific TCP connection, when the client reconnects, there are state management operations like file reopen, which the client needs to do for all those 100 handles, assuming they are persistent handles. Now, with multiple TCP connections, if there are network hiccups and one connection goes down, you still have additional 3 connections, which allows you to continue serving traffic for that specific session, thereby reducing the number of state management related changes and focus more on IOs like read and write. Because we now allow 4 TCP connections to serve traffic from the client, there is better cost optimization because the client VMs can now be used up to their full capacity. Multi-channel for SMB with the improvements in throughput and IOPS is what we are doing now is we are rolling out multi-channel to be enabled by default for all premium file accounts because of the benefits that the clients can get. These are just some numbers that I wanted to share with you for big size, for sizes 1 MB and greater, you see read throughput gains of more than 2x. For write, you see more than 4x improvement for SMB multi-channel. And for NFS and connect, for big sizes like 1 MB and more, you are actually able to see more than 3 to 4x improvement across both read and write throughput. The last one which I wanted to share with you guys was the lease break optimization. Imagine a scenario, and we ran into this, was at the top of the hour, multiple VMs would try to actually connect or open a file and request exclusive lease. I believe they're trying to implement some sort of mutual exclusion, and whichever VM ends up getting the exclusive lease will actually end up performing some sort of workload. Now, what ended up happening over here was those old Linux clients. Let me take a step back, right? So the picture is you have a single client which will come and request an exclusive lease, will get the RWH lease back from the server. You have a second client which will come and request an exclusive lease, but both of them will be broken down to RH. For that, the server has to send a lease break request to the first client, and an old Linux client was not responding back with the lease break acknowledgement. As a result of it, we were waiting till the timeout period to serve the file open request for the other clients which were trying to access this specific file or open handles against this specific file. So what we also observed was, as soon as that handle was opened, within some time the handle was being closed back again. So now at the top of the hour or after some predetermined time, we would see this workflow again, wherein simultaneously multiple clients would try to actually again open a handle requesting exclusive lease. Then we'll end up breaking the lease, but after some timeout, and that would cause an increase in latency. And then the client, all of them would just close the handle again. And we would see this over and over again. So what we did for this was, we built an in-memory cache of the file's last lease state and some heuristics to know that if a handle, the lease state is going to be broken, then we are not issuing them an exclusive lease. We just give them an RH lease to begin with. So the benefit of this was, we reduced the number of lease break requests which had to be sent from the server to the clients, and reduced the need to wait for an acknowledgement from an old client which was not sending it to us, and thereby improving latencies for our file open calls. I would like to bring Rina to the podium for the next set.
Thanks, Utsav. So thanks, Sutsa, for deep diving into some of the interesting challenges in the high availability and the performance areas. We'll next dive a little bit deeper into the security area. So in the security area, as you know, a single security solution doesn't satisfy the high security needs that we have in today's day and age. Security needs to come in multiple layers. You need to have network security, you need to have role-based access control at your server level, and you need encryption at rest in transit, and the files and directories needs to be ACLed. So all of these security layers we built ground up, and one of the areas which I would like to dive a little deeper is the authentication. In SMB and NFS, one of the protocols that we use as authentication protocol is Kerberos. Now, when it comes to cloud, the native protocol that is typically supported is the OAuth. But when it comes to SMB and NFS, we had to think about how to provide this Kerberos in cloud. So when you think about from the lens of a customer, right? When a customer is moving to cloud, their journey doesn't go overnight from on-premises to cloud. Typically, customers, they have their on-premises data center which are running their file servers. And the data center is contracted for, say, 5 years, 10 years. And typically, when they are closer to their data center contracts coming to an end, they start thinking about moving their file systems to cloud. So at that point, they want their file systems to be in cloud, but they want their identity system to remain on-prem because rest of the workload is still remaining on-prem. So identity on-prem and file systems in cloud. Then slowly, they want to start syncing their on-premises identity system into the cloud identity system. And at least for the file system workload, have the hybrid identity approach where the primary identity system is still on-prem. That identity system is syncing the users and groups into cloud. And whenever the file system is being accessed, that is being accessed through the cloud identity or the hybrid identity. And this third one is when you completely cut over and move completely to cloud. We have seen some customers start just go to the number 3 directly because they are building some born in cloud workloads and they need not go through that journey. But it's typically 80-20 scenario in that way. So for the first one, we offer an on-premises AD access to the file shares, where your on-premises AD is acting as your domain controller. If you have a client in the cloud, that client will be connected and domain joined to your on-premises AD, and you will be accessing your files using the on-premises AD identity. This is the one that we had to uniquely think about, because what happens typically is if you see any providers, any hyperscalers, the identity is either completely on-premise or completely in cloud. But this was the one area where we had to think a little harder and deeper on how do we support customers who are still in this hybrid phase, where they still want the primary AD to be on-premises, but they do not want a very complicated network connection which is set up between their on-premises and the cloud, and they need not be in the same network boundaries. So we introduced Entra Kerberos. This is a setup where the user VMs can completely rely on the Entra. Entra is our Azure AD, which is renamed to Entra now. So the end users or the customers who are having client VMs deployed in cloud will be able to access their file systems using just Entra because of the Entra Kerberos feature that was built. And then the next one is completely in cloud. So there are two things in this area. One is we provide Entra DS support, where Entra DS acts as your domain controller, and the identity for your file system is provided through Entra DS and Entra. We are also working on cloud identities, where the second one is the hybrid identity, and the third one is completely cloud identities, which are planned to be supported in the near future. So I will dive a little deeper into what is the typical user experience when they are trying to mount a file share using Entra Kerberos. So there were two things that we had to build for enabling the Entra scenario where the Entra is acting as a KDC. First, we had to go enable Entra to talk Entra Kerberos like a KDC, act as a KDC. And the second, we had to enable the Windows client VM to understand cloud identities and cloud SIDs. So with those two in place, here is a typical customer setup where customers have on-premises AD, and which is syncing to the Entra with Entra Sync. So all the identities which are being created on-premises are being synced into the cloud. And there is a VM, which is an admin VM, say for example, which is joined to this on-premises AD domain. Now, this admin VM can go and create a storage account in cloud. What that does is it will automatically create an object in Entra with that storage account. And then the admin can go and set up the ACLs on the files and directory level for all the users in the system. This is required because the SID to UPN mapping is available in the on-premises AD, and the admin needs to leverage that for setting the ACLs for all the users. So now, once all of this setup is done, now when a user comes in and wants to mount a file share, a client VM which is joined to Entra completely in cloud, they will be already having the TGT because they are joined to Entra. Using that TGT, they will ask Entra Kerberos for a service ticket, and Entra Kerberos will encrypt the service ticket with the with the storage account token that we have, the storage account key that we created when we created the storage account. It will look for the storage account in the storage account object that we had created during the storage account creation. So with those two things, it will just encrypt that service ticket and it will send it back to the client. Then the client uses that service ticket for SMB session setup and goes to the storage account. Now the storage account, if the storage account is able to decrypt that ticket, it will create an access token, and it will create an access token and embed it with all the SIDs that came into that service ticket. Using that, now at the share level, the permissions are completely based on role-based access control, which is based on the OIDs. So over here, some kind of mapping needs to happen between the OID and the SID, and that happens over here. And then the roles are determined based on like, is it a contributor, is it an elevated contributor, is it a reader, and based on that, the access is determined. And from here on, once that access is determined and the user has the SID which falls into the authenticated role, the NTFS permissions and like the ACLs take over, where now the files and directories are all determined based on the ACLs that is available for the file system. So with that, this is a typical cloud VM, but the same flow is available to any VM on the internet. So even if the user VM is outside of the network which is on their on-premise network, they will still be able to access the cloud file share just through the internet using the Entra Kerberos. So with that, switching gears a little bit, we will talk about the third protocol that we have in addition to the SMB and NFS protocol. So the third protocol is the REST interop. So this is REST, which is able to access the same data and perform the data plane operations on the same data, which can be accessed from SMB and NFS. So for that, there are certain reasons why some customers would want to use REST. Number one reason is REST is by nature stateless protocol, and SMB and NFS are stateful protocol. So when it comes to statefulness, it comes with some amount of additional chatter over the wire. Now, when you talk about on-premises system, the file server and the client VMs are typically located next to each other. But when it comes to cloud, the latencies are higher compared to the on-premises when it comes to network latencies because just of the law of physics. So the number one reason is chattiness. Number two reason is when you think about network configurations, what we see is SMB and NFS require special port configurations. SMB requires port 445 and NFS requires 2049. So explicitly going on network and enabling the firewall settings may not be available to end users. So for having like that lack of barrier to entry and like just being able to access the file shares directly from the internet, that's the luxury that you get with REST because it goes over 443. And the third is Kerberos. So typically when you have users and groups like within the system versus you have an ISV who is outside of the identity system, the OAuth is an easier protocol to be able to set up as opposed to Kerberos. So that's the other reason why some customers may want to use REST. And think about a scenario where statelessness is just fine. Like think about backup scenario. Backups are usually taken from snapshots, which are read-only copies. And all you're doing is copying the data from that, that snapshot into a durable location. So for that, statelessness is just fine. And most of the ISV scenarios, more or less, we have seen like, multiple of them fall in this category. One success story that we have seen with REST is Azure File Sync. So I'll go over that and I'll explain a little bit on what Azure File Sync is and then talk about how Azure File Sync leverages REST. So Azure File Sync is nothing but an on-premises cache of the data sitting in the cloud. So think about it that you have Windows Server on-prem and the Windows Server on-premises, which is acting as your file server, needs to be replaced or needs more capacity. So at that point, you can decide to just turn the Windows Server into an on-premises cache by simply installing the Azure File Sync agent. So once you install the Azure File Sync agent, you can convert your on-premises Windows file server into a cache which serves SMB and NFS traffic, and users can start accessing through SMB and NFS. What happens when you install the file sync agent is it will bring down the metadata instantly from the cloud, but the data still remains in cloud. So when the metadata is there on premises, customers can just click on their files, and then at that point, the file will tear down, and the file will be available for serving from on-premises. And the cache keeps on building as the time progresses, and then the colder data is tiered back into the cloud. And now the customer does not need to maintain any of their backups or application on-prem because that is all happening in cloud. And in case of a disaster, if you lose your Windows file server, you can seamlessly bring another file server up by installing the Azure File Sync agent, which will start doing which will do a rapid DR and bring down the metadata again. And then over the time, the cache starts getting populated. So all of this was possible because all that cloud tiering that you saw, which was happening between the Azure Files and the on-premises server, was happening through REST. The Azure backup that you saw was happening in cloud. All of that was going over REST. So while customers can access their SMB and NFS from Windows desktop on-prem or from the SMB protocol in cloud, the rest of the things like the syncing of cloud tiering and the Azure backup was happening from the REST protocols. So just summarizing, Azure Files is a distributed cloud file system in cloud which provides access to Windows, Linux, and Mac through SMB and NFS protocol. We provide on-premises caching capability through Azure File Sync, and the clients can be either in cloud or on-premises. The client can be either VMs or containers. So if I have to say 3 things that you can take away from this session is cloud file systems are one of the easiest way to start deploying and start testing cloud out because they are lift and shift. They are the traditional protocols that are supported in cloud. For ISVs and partners, we have seen very good success with REST APIs. So that additional layer of REST APIs is available. And if you are interested in either building a value-added service, like in the areas of disaster recovery, data protection, scanning, security, AI, ML, just come talk to us. We'll be happy to partner with you. And the last one is, from whatever you see today, please provide us feedback, help us improve our product. We would love to learn more from you, and we would love that if you could learn more about Azure Files and just watch the other Azure sessions in the SNIA conference. So with that, I really want to thank you for staying beyond the noon while the lunch is out there. Wonderful talking to you, and thank you very much. You can reach out to us at azurefiles.com or at microsoft.com or on our LinkedIn. Thank you very much, and we're open for questions.